Welcome to Techno Sapiens.
Picture this. You're looking out your window during a massive storm. The wind is howling, those huge utility poles are swaying wildly, and suddenly, boom. The night sky lights up with this blinding, terrifying flash. You know the one. Have you ever wondered what exactly happens up there when those massive power lines swing together and actually touch? Well, in this explainer, we're unpacking the raw, explosive mechanics of our electrical grid to discover exactly why power lines create those massive flashes.
Subscribe to Techno Sapiens and learn something new every time.
So what actually goes down when those lines physically touch? I mean, when 60-mile-an-hour winds whip swaying lines into each other, does it trigger some massive explosion? Does the entire city's power grid just catastrophically fail in a chain reaction? To really grasp the reality of this dramatic event, we first need to understand the invisible forces flowing right over our heads. Okay, let's dive into this. In a standard three-phase power system, phase A, phase B, and phase C aren't just redundant backup wires. They each carry alternating voltage that is shifted in time relative to the others, meaning at any given millisecond, each wire sits at a completely different electrical potential. And normally, these differing potentials are kept safely apart by a really simple but highly effective insulator, open air. As long as they keep their physical distance, the whole system works flawlessly. But maintaining that distance requires a staggering amount of intense engineering. Utility companies are constantly fighting a war against environmental threats. They're using long crossarms and heavy-duty insulators specifically to combat wind, heavy ice buildup, intense heat that causes line sag, lightning strikes, and unpredictable mechanical movement. If any of those factors overpower the engineering and cause the conductors to swing just a bit too close together, that protective barrier of air is instantly compromised. Think of voltage as essentially the electrical pressure driving the current. If you have two wires with a significant voltage difference, like a huge difference in electrical pressure, and they suddenly physically touch, the rules change in a fraction of a second. The electricity instantly abandons its normal route. It just forces its way through a brand new, very low resistance path directly between the two conductors. A great way to visualize this chaos is by comparing the electrical grid to a massive highway system. Under normal operation, it's a smooth highway. Electricity travels safely along its planned route, flowing through controlled loads like your local transformers and eventually down to the appliances in your home. These loads act like traffic regulators, right? Keeping everything moving at a safe speed. But a fault condition, that is like opening a dangerous, totally unauthorized shortcut on the highway with absolutely zero speed limit and almost no resistance. Suddenly, all that massive electrical traffic rushes into one single location, completely bypassing the normal loads entirely. And this brilliantly illustrates just how much energy power systems can supply the moment this shortcut opens, creating what we call a short circuit. Because the intended path is bypassed, an enormous, unregulated amount of current flows through that fault in literal milliseconds. Because our power systems are designed to supply vast amounts of energy to entire cities, the sheer volume of power dumped into the shortcut is absolutely staggering. The current spikes to dangerously high levels almost instantaneously. So, knowing all that immense power is suddenly surging into one tiny spot, why exactly do we see a massive flash of light? What creates that terrifying visual that lights up the whole neighborhood during a storm? Well, the secret lies in the physical mechanics of the wires themselves. In high winds, the wires rarely just touch and stay welded together. Instead, they violently slap together, and the momentum pulls them slightly apart, creating a microscopic gap. But remember that massive spike in electrical pressure we just talked about? The voltage is now so incredibly high that it simply refuses to be stopped by that tiny space. The intense electric field literally breaks down the insulating properties of the air itself. It forces the electricity to aggressively jump across that broken down gap. And this violent jump, that is what we call an electric arc. The electricity is forcefully bridging the physical distance between the two swinging cables, just desperate to keep the current flowing. Here's where it gets crazy. The air in that gap doesn't just step aside. It undergoes a radical transformation. The extreme voltage ionizes the air, turning it into an extremely conductive state of matter known as plasma. This plasma path is the true culprit here. It's the reason why, when you look up during that storm, you don't just see wires touching. You witness blindingly bright sparks, an intense flash of glowing plasma, and a localized release of extreme heat. And the physical fallout of this electric arc is completely staggering. The plasma arc is unbelievably hot. The intense current rapidly heats the surrounding air and metal to the point where the thick metal conductors themselves can actually melt or instantly vaporize right at the fault point. Plus, this sudden, extreme heating causes the surrounding air to expand violently and rapidly. That rapid air expansion, that's what creates the loud, terrifying explosion-like bang that rattles your windows. You are literally seeing and hearing the raw, uncontained fury of a plasma arc. Now, consider the multiplier effect for a second. If phase A touching phase B causes the massive fault we just covered, imagine the catastrophic potential if all three phases swing and touch simultaneously. With all three out-of-sync voltages colliding with incredibly low fault impedance, the potential fault current multiplies. It becomes an exponentially more destructive event, pushing the physical limits of the infrastructure to the absolute brink. Let's move to T and see how this builds, because thankfully, we aren't left defenseless against these massive electrical explosions. The grid has a remarkably rapid defense system. Protective relays act like high-speed traffic controllers, constantly monitoring the current and voltage on the lines. The absolute millisecond they detect a fault, they trigger circuit breakers to open up and mechanically disconnect the damaged section. The immediate result? The equipment is protected, the explosive fault is isolated, and the problem is stopped before cascading and shutting down the rest of the electrical grid. I absolutely love this quote from our source material because it perfectly summarizes our journey today. Electricity is powerful, but protection systems are even smarter. We started with a massive voltage difference, watched it bridge a tiny air gap to create terrifying, superheated plasma, and finally saw how incredibly fast mechanical reflexes step in. These systems are meticulously designed to detect the invisible surge and cut off the physical road before the raw power of the grid destroys itself. Which leaves us with a final thought to ponder. Every time a storm rolls in, the wind howls and the lights flicker, it begs the question, are we entirely reliant on these hidden mechanical reflexes to survive the raw, explosive power of our own grid? It's a pretty sobering reminder of the invisible, high-stakes battle happening right above our heads just to keep the modern world running. Thank you for joining me for this explainer. I hope it sparks some curiosity. And as always, keep asking how the world around you works.